Okay, so now the recording I think is on. And first, let me briefly introduce myself. So I'm currently a senior lecturer at RSFS at ANU, and my research interests include covariance regression modeling, network data modeling, financial statistics, environmental statistics, and dependent data analysis. So now let me start my talk about network influence analysis. So this work is a joint work with my long-term collaborators, Professor Ronghua Luo, Professor Wei Lan, and also Professor Chiling Cai. And Professor Ronghua Luo visited our school once, I think in 2018. And so in my talk today, so this is the overview. The outline of today's talk is kind of very standard for statistic talks. And also I noticed some finance academics are also here. And so this talk is basically based on these two papers. And the first one is the recent accepted Statistics Sinica paper, Network Influence Analysis. So if you are interested, you can check check online. And the second one is the one I just submitted. So I will briefly mention the connection between these two, but I will focus on the first one. Okay. So firstly, let me just introduce my motivation. I think this work is not a very difficult work. It's actually very simple work. However, I think the motivation is kind of a little bit longer compared to the standard statistic talks. So our work is motivated from the social network sites, so including like Facebook, Twitter, and also TikTok. And those websites are extremely popular nowadays. And also those websites possess a lot of information online. And I think that's also one excuse that President Trump wants to expel TikTok, because obviously TikTok possesses a large amount of information, especially personal information of US. So usually for those social network sites, they actually have two kinds of data. So the first kind of data is related to users' information, and usually in social network we call a user a node. So in that case, for those social network sites, they have the node-wise information, like the personal information, age, occupation, like or dislike, so on and so forth. And the other kind of data that those social network sites have is the we call it edge-wise information. So that basically means those relationships between different users. So for instance, for the Twitter network, we have the follower-followee relationships. And also on Twitter, you can actually comment, sum up, and also forward the other users' tweet. So that's also kind of network or the edge-wise data, I think, which can be obtained from the social network sites. So because of those development of the social network sites, so obviously those data are available now. So now the problem is that how to kind of analyze those kind of data such that we can make value for the data analysis. So that's the question we kind of want to answer. And before we kind of answer that question, so firstly, I just list some applications by using those kind of social network data, I think in real applications, especially for those researchers. And the first one is from the marketing example. And the marketing researchers just find that obviously it's more effective to promote new products through the social network sites. And usually if for those advertising agencies, if they want to promote something, they can directly request the most influential user in the social network to promote, so that can give a better promotion result. And the second example is from the finance. So in finance, they just find that some central investors from a social network can earn higher returns compared to those investors who are not in the central. And also in the management, those management researchers also find managers' social networks can actually affect the corporate policy decisions. So basically, if we have those kind of node-wise information or edge-wise information, we can actually make a lot of applications in both academic and also in industry. So that's the background. And in order to model the social network data, so firstly, we actually need to consider how to transform the edgewise information or the network data into some mathematical notations. So here we just introduce a notation which is called adjacency matrix to basically describe the network structure. So in social network analysis, basically network structure and adjacency matrix are equivalent. So in order to define this adjacency matrix, so let me just use this figure to help you understand. So let's just focus on node 1 or user 1, user 2, and also user 3. Okay, and also we can imagine that they are in a Twitter network. So in the Twitter network, the classical network information is about the follower-followee relationship, right? So in this specific case, node 1 or user 1 follows user 2, and also user 2 follows user 1. So in that case, we can use these indicator variables A12 and A21, and we let them be 1 to represent that 1 follows 2 and 2 also follows 1. However, if we have a look at nodes 2 and 3, so we find that node 2 follows 3, however, 3 does not follow 2. So in that case, we have the indicator variables A23 equals to 1, but A32 equals to 0. And last, if we have a look at the node 1 and also node 3, so there is no relationship. So in that case, we have A13 equals to A31 equals to 0. So after we define those indicator variables, we can actually put all of those indicator variables in a matrix. So that basically constructs the adjacency matrix. So really, if the adjacency matrix is given, then the network structure is given. So that's a way for us to involve the network structure in the modeling. That's really the first step. And really, for the completeness, we let the diagonal elements be one. So that's purely for convenience. So after we properly define the adjacency matrix, then let's just look at the basic model. So the basic model in social network analysis is actually from spatial econometrics. It's called spatial autoregressive model. So in order to introduce this spatial autoregressive model, firstly, instead of the adjacency matrix, so here I give this 5x5 example of adjacency matrix, and we basically consider the normalization, and here is actually the row normalization, and then we can obtain a weight matrix, and this weight matrix is the row normalized adjacency matrix. So to see the reason why we consider the row normalization for this adjacency matrix, so let's just look at some specific example. So let's look at example for the node 2. So let's look at the row for the node 2. So the row for the node 2 just represents that node 2 follows node 1. So we have 1 here. And also node 2 does not follow node, so here we just assume all the diagonal elements being 0. And node 2 follows node 3, so we have another 1 here. And node 2 follows node 4, we have also 1 here. And node 2 does not follow node 5, so we have 0 here. And because node 2 follows three users in the network, so intuitively we can understand that so the node 2 should be influenced by node 1, node 3, and node 4. And each of these 3 nodes, 1, 3, 4, has influence on the node. However, because there are 3 people, so in that case, 1 can only influence node 2 by 1/3. So that's the reason why we consider the row normalization to give this kind of intuitive interpretation of the influence. And usually, if a node follows more people, then for the user that the node follows, so that user usually has a really low influence, right? So in this case, because node 2 follows 3 people, so each influence is 1/3. However, if we have a look at node 1, because node 1 follows only one person, so in that case, that one person has influence as 1. So after defining this row normalized adjacency matrix, then we can introduce this very classical model. So this classical model is to use firstly to model the node-wise information. So we consider we have some node-wise information y1 to yn as our response vector, and then we just involve this row normalized adjacency matrix in our modeling. So to see the interpretation of this model, so let me still use this example. So in this example, it's quite clear that if we have a look at the row 2, so we can find that the row 2, the response of node 2 is determined by the response of the other nodes, node 1, node 3, and node 4. And remember that those nodes are actually the nodes that node 2 follows. And also we have the 1/3 here to measure that each node can only has 1/3 influence on the Y2. However, obviously there is a decay in the network diffusion. So in this case, we have this decaying parameter, or we can call it the network effect or network autocorrelation parameter lambda here to measure the decay of the network diffusion. So that's the reason why this model is so popular, because of its interpretation, just like the simple linear regression or the linear regression model, because the interpretation is quite clear. So this model is widely used in the social network analysis literatures. And for most literatures, they just estimate this autocorrelation parameter lambda, and then they can kind of measure when the network effect for some specific network online. However, I think a very obvious limitation for this kind of modeling here is that basically in this model assumes that all the influences here can, or this decaying parameter lambda is homogeneous. So that means this kind of influence is the same for all different users. So in this case, we just extend this kind of simple modeling by involving the heterogeneity in the influential index. So here we just consider that for node 1 can actually influence node 2 via the influential index lambda 1. So clearly you can see here that lambda 1 measures the influential power of Y1. So if Y1 has a higher influential power, then obviously it can influence node 2 more via this parameter lambda 1. And similarly, we can have more parameters. So by extending this simple homogeneous spatial autoregressive model by involving the influential powers of different nodes, so then we just propose this adaptive spatial autoregressive model. And obviously, even though I do think this extension is quite simple, but it can give us much better application results or application interests. So that's the basic idea of this modeling. And so, so the next step is just to write this idea into a matrix form. And in this matrix form, we will find that in order to involve those influential powers or influence indices in the modeling, we need to multiply this diagonal matrix lambda. And so for this diagonal matrix lambda has all the diagonal elements being those influential indices. So in this case, we have our adaptive SAR model. So later, I'm going to investigate more details about this model. But before we proceed, I want to mention about the difference between the network modeling and the spatial modeling. Because even though this model is mainly proposed for the network data, however, I have to say this model is originally from the spatial econometrics modeling. So, but even though the model looks quite similar, but there are some differences between the network modeling and the spatial modeling. So the first difference is about this weight matrix. So earlier I have mentioned that this weight matrix is actually from the adjacency matrix. It's the row normalized adjacency matrix for the network data. However, for the spatial data, we usually have the W as the kind of the distance matrix or the similarity matrix. So that's the first difference. So the second difference here is that for the social network data, usually we do not have the concept of locations, because if you have a look at each node in a social network, it's not necessary that we can have a location to correspond to that node. However, it's totally different story. So for social, spatial data, we can actually have a location. So because there is no location, so in this case, so the classical dependence structure from the spatial statistics or spatial econometrics cannot be used in the social network modeling because we do not have the locations. And for instance, in spatial statistics or econometrics, we use the spatial mixing, which is used to describe the dependent structure of the responses. However, in social network analysis, we cannot. So what we only have here is just this model. We can only base on this model to use the dependent structure given this model to get our properties of the parameter estimation. So that's the main difference between the network data modeling and spatial modeling. So, so I have mentioned about this right multiply, and this right multiply is actually from the interpretation given here. So let's still look at the second row. So here, the right multiply of the diagonal matrix lambda consists of these parameters lambda 1, lambda 2, lambda 3 until lambda 5 in this specific case. And this lambda 1 measures the influential power of node 1. So let's just stand at the point of node 2. So in this case, lambda 1 is actually from outside, right? Because it's actually from the node 1. It's from, so in this case, we actually call it the outward influence from the node 1. But in contrast to the outward influence, we can also define something called inward influence. So if we want to define inward influence, we actually need to put this lambda matrix at the front of W to consider this left multiply. And in this case, the inward influence is actually used to measure how easy this node, for instance, node 2 can be influenced by the other nodes. So if we have the left multiply, we have the inward influence. However, if we have the right multiply, we have the outward influence. So these influences are totally different. And it's actually in my recent work. So I just submitted this work. And obviously for this model, we have the identification problem. But the interpretation is quite similar to the influential, to this model, to this adaptive SAR model. So I think I only mentioned about this inward and outward more complicated model here. So instead of this kind of standard cross-sectional data form for this adaptive SAR model, we can actually extend the cross-sectional data into more complicated, like the spatial temporal model or the panel data models. So so for spatial temporal model, it's the spatial temporal model in econometrics. So it's quite different from the spatial temporal model in statistics. So basically, for spatial temporal model in econometrics, they just consider this high dimensional time series model. And for this kind of model, I think this model is proposed by another reference. And what I can say here is that this is from a different group of researchers, and we almost submitted our paper based on quite similar ideas at the same time. However, they just published more quickly. And this is about the spatial temporal model extension. And we can consider more extensions like the panel data or dynamic panel data model. Obviously, I haven't done this. And also, obviously, it can provide more applications. But from the theoretical point of view, I do think the theoretical properties of this model is kind of very similar to this standard cross-sectional model. So if you are interested, you can actually contact me and we can chat more about the possible extensions of this model. And after I spent like 20 minutes to talk about the motivation, so now let me talk about some details about this modeling and also the estimation properties. So in our paper, we instead of the influential index or influence part in the model, we also consider the standard regression part, such that this model can be applied more widely, I think, in real application. And here, so the problem here is that we only consider this cross-sectional data. So that basically means we only have n equations in this model. However, in total, we have n parameters for the influential indices and also p parameters for the covariates. So that means we have n equations, however, n plus p parameters. So in this case, we have too many parameters to identify, so we cannot estimate these influential indices. So there are a lot of ways to deal with this kind of problem. So the very classical high dimension way is just to consider a sparse structure for these influential indices. So in that case, we can actually consider lasso or fuse the lasso to consider the structure of this lambda 1 to lambda n. So that's one possible way to solve this problem. However, we didn't follow this way. We just want to make this work more applied, such that the applied people can use this model more easily. So we just consider that because lambda I just measures the node's influential power, so obviously lambda I should be determined by its own attributes. And here I just give this example. And President Trump is very influential, and obviously because that he is the president because of his occupation. So in this case, this influential index can actually be interpreted or can be determined by the other attributes or by the covariates. So it's very natural for us to use the covariates to model this influential index. So that's also a very straightforward idea from the regression modeling. So in this case, we just try to reparameterize this lambda I and then involve this occupation or the other attributes in the modeling. And we call these attributes by using this terminology, we call it influence covariates. So we can input the occupation or the age or so on and so forth, and the other personal information as the influence covariates. And the next step, we just parameterize the influential power by using those covariates and also a link function. So this is also directly from the generalized linear model idea. So here, in order to get a better interpretation, so we consider this link function is a strictly monotone. So in that case, this beta coefficient can actually measure the how each influence covariate determines the influential power of some specific node. So in that case, this beta has a very straightforward interpretation as the standard linear regression model. So here we also notice that if we consider, except for the intercept, if we consider all the other coefficients equal to 0, then this model just reduces to the classical spatial autoregressive model. So based on this fact, we know that our model obviously is the extension of this classical spatial autoregressive model. And also, if we want to test whether or not we should use our model or the spatial autoregressive model, we just need to test all the other coefficients except for the intercept equal to 0. So that's our parameterization for our influential indices. And now let me just introduce some link functions. So here I just give some examples of the link function. So kind of I just directly copy it from the generalized linear model. The first one is a logistically linked, and second is probably linked, and third is from the extreme link from the extreme distribution, and the last one is from the log, I think Poisson log linear regression from the exponential link. So all of these link functions are strictly monotone, such that we can have a very good interpretation for the coefficients beta. And also we can consider some non-parametric modeling or semi-parametric modeling, like the semi-parametric single index model. So that's the work I'm working with. So in that case, we do not need to assume this parametric form for the link functions. And after we parameterize our influential indices by using the link function and also those covariates, the next step is just to consider the parameter estimation of those coefficients, especially coefficients beta. So in order to investigate the estimation, so first we just consider the standard maximum likelihood estimation. And in order to obtain the maximum likelihood estimation, what we need to do here is just to suppose our random error follows a normal distribution, a multivariate normal distribution, and then we can just write down the log likelihood function in this way. And because we have this log likelihood function, including the alpha is actually the mean regression coefficient, and also we have beta is from the influential indices coefficient, and also we have sigma square. So sigma square is the standard is the variance of the error term. So in this case, we can write down the log likelihood, and in order to estimate it, we just adopt the very classical procedure, the concentrated likelihood or profile likelihood in statistics. So what we need to do is just to fix, which is just given beta, and then we maximize the log likelihood, and then we obtain the closed form solution for the alpha and sigma square. And obviously, because of these closed form solutions, we consider to adopt this method to help us to reduce the computational complexity. And then we just input those expressions of alpha and also sigma square in the expression of the log likelihood, and then we just maximize the log likelihood by using directly maximizing beta. And after we maximizing beta, we just plug in those beta heads back, and then we obtain our estimation. So this estimation procedure is kind of very standard. I do not think that's nothing quite special. So instead of the normal data, sometimes we also have the non-normal data. If we have the non-normal data, we can still use this log likelihood function, even though this log likelihood function is evaluated at the normal distribution assumption. We can still use this log likelihood and then obtain the maximum likelihood estimation. And actually, we can find that even if the data are not normal, but if the data have finite 4 plus etas order moment, then we can have a very good estimation for theta hat. So in that case, we call it the quasi-maximum likelihood estimation. So in my talk today, to simplify the notations, I just show the results for MLE, but for QMLE, if you are interested, you can find those results in the paper with involving the third and also the fourth order moments. So usually, if we consider the QMLE, because for the non-normal data, we usually have non-zero third order moment and also unknown fourth order moments or kurtosis. So in that case, those moments will be involved in the asymptotic distribution in this specific case. So now let me just show some theoretical results. So I do think the theoretical result is also kind of standard, but we can only make use of the dependent structure for the network data in deriving the asymptotic results. So that's the only thing we need to be very careful about. And here, for the normal distribution, is kind of quite straightforward. We just need to compute the Fisher information matrix. And for this Fisher information matrix, because we have 3 parameters, we have alpha, beta, and sigma square. So we have 3 by 3 block Fisher information matrices. And by some derivation, I think it can be done. And the one block is just a standard linear regression, if you can notice, and also the 3-3 block is also kind of standard linear regression to estimate the variance of the error term. So the problem here is about this alpha beta block and also beta beta block and beta sigma square block. And for these blocks, I think after some derivation, you will find that those blocks are just from the traces of some row normalized adjacency matrix and also the other matrices, and also our influential in the index matrices. So that's just some kind of basic derivation. So after this derivation, we can obtain the theoretical properties. And so in this case, we can obtain our asymptotic normality for our maximum likelihood estimation under the normality assumption. And here it's just directly converges to the normal distribution with mean 0 and also covariance matrix, the information matrix inverse. That's kind of standard. But for the non-normal data, we also derive the result in the paper. And for the non-normal data, we will have a sandwich matrix instead of this information matrix. So that's the only difference. So after we obtain the parameter estimation, now let's just consider to use this asymptotic distribution to help establish the statistical inference in real applications. So in real applications, we care about a lot of problems. And one problem we care about here is that whether or not we should use our model or the classical spatial autoregressive model to test the homogeneous of the influential indices. So in this case, we just need to test all the influential indices equal to some constant lambda. And because we have the strict monotonicity of the link function, so it can be equivalently to test that we just need to test whether or not all the beta coefficients equal to 0 except for the intercept. So in this case, because we can transform our assumption, the homogeneous test assumption by homogeneous null hypothesis into this beta non-hypothesis. So straightforward speaking, we just consider the test related to a lot of coefficients which can help us to accomplish this test. So because we have this observation, so we can consider the kind of the standard 3 basic tests, I think, in statistics to accomplish this application. So I think this kind of standard. So the first one is the likelihood ratio, and the second one is the word test, and the third one is the score test. So in classical statistics theory, these 3 tests are asymptotic equivalent. And in our case, these 3 tests are asymptotic equivalent, obviously, for the normal data. And you can find that under the normal data, these 3 tests all converge to this standard chi-square distribution. So you can also have a look at the other score test result. However, for under the non-normal data, even though these 3 tests are still equivalent, but there is some difference among these 3 tests. And first difference here is that under the non-normal data, for the likelihood ratio test, the test statistic is not asymptotically chi-square, it's actually weighted chi-square for the likelihood ratio test. And for the word test, it's still the same because word test is kind of very straightforward from the asymptotic normality. And as for the score test under the non-normal assumption is also weighted chi-square, but not chi-square. So by using these 3 tests, any one of these 3 tests, we can actually obtain our result, whether or not we should use the homogeneous influence or we use the heterogeneous influence. So the finite sample performance of these 3 tests are investigated in the simulation studies. And if I have time, I will briefly mention about that. So another application here is that we want to make use of these influential indices such that we can kind of obtain the subgroups of the nodes by using these influential indices, or we want to cluster the different nodes by using the influential indices. So here I just directly give this test, but what we want to do, so let me just show you a plot. So what we want to do here is that we just want to use these influential indices to cluster different nodes in this social network. So obviously in this plot we have 4 clusters, and the cluster 1 has the largest influential index, and the second cluster has the second largest influential indices, and also we have third, and also we have the 4th cluster. So basically for the 4th cluster, there is basically no influential power for these clusters. So if we can get some plots like here, then for instance in marketing, what we need to do here is just to identify this most influential user or node in the network, and then we just request this user to help promote some product for the advertising. So in this case, I do think this plot can give the I think practitioners more application by using this model. So now let's just talk about the details about this test. So the detail of this test is basically to test subgroups of those influential indices are equal, and because of the monotonicity of the link function, we can actually transform this non-hypothesis into the hypothesis with respect to our parameters. And what we need to do here is just to specify some matrices, and then we just test the matrix product just equals to 0. And usually if we have this kind of linear combination test, we can directly use the word test, or we can use the likelihood ratio or the score test. That's kind of very similar to what we have done earlier. However, the application, as I mentioned here, is very important. It can help us to identify influential nodes in a social network. So I think that's almost all the theory part. And let me just talk about the real data analysis first, and then if I have time, I will talk about the simulation studies. So in this real data analysis, what I want to do here is that I just want to study the information network for the mutual funds. And in a lot of finance literatures, they just find the existence of this information network, and also they theoretically and also empirically find the effect of this information network among the mutual funds. And also they those researchers also find that the mutual fund family network can have positive effect on the member funds, the performance of the member funds. So in this case, from the theory and also from empirically, we both find that this information network can have influence on the performance of the mutual funds. So in that case, it's quite natural for us to study this information network and study how this information network affect the performances of mutual funds. So that's the background. And so here in this specific real data example, I just want to investigate the influence mechanism. So basically what I want to do here is that first I want to identify most influential mutual funds in the mutual fund network. And secondly, I want to find that what kind of attributes can determine the mutual fund's influence. So if we can find the mutual funds with those attributes such that the mutual fund has a really large influential power. So in that case, usually as investors, I can actually notice that kind of mutual funds with those attributes more closely, or as a regulator, I can I can also monitor those mutual funds with those attributes more closely, because usually those mutual funds have very large influential power on the other mutual funds, so that will possibly bring a shock or bring a drop or bring increase in the whole market. So in that case, what we need to do here is that we need to consider the mutual funds performance, and also we need to model the information network of the mutual funds to explain the performance of the mutual funds. So usually the effect of the network on mutual funds here, which has been studied well, is the effect on the cash flow of the mutual funds. So that's the reason why we use the cash flow as our response variable, because it's well studied, the effect. So here we have the cash flow as our response variable. And the next here is that we need to find the information network for mutual funds. So how to construct the information network for the mutual funds? So here we give this example from the Chinese actively managed open-ended mutual fund data. And in this data, we just define this information network by using this adjacency matrix. And each entry of the adjacency matrix Aij equals to 1 if two mutual funds invest at least 2.5% to the same stock. Otherwise, if the two mutual funds do not invest 2.5% to the same stock, then we consider that there is no relationship between these two mutual funds. So basically, we use the same investment as to connect different mutual funds and use it to construct the information network. So that's also quite natural in the finance literatures. And after we obtain this adjacency matrix based on this information network, then what we need to do here is that we just search the classical mutual fund literatures to input this fund size, age, return, and alpha in the mean covariates, because those covariates are, I think, are studied well in finance literatures to have influence on the mutual fund cash flow. And instead of the mean covariate, we also have the influence covariates. So for influence covariates, usually from our intuition, we consider something like degree. So degree just means the total number of links connecting to the node. So usually, as our imagination, if some mutual fund has a large network, so that basically means it connects to more nodes, then it should have a larger influence compared to the other companies. So that's what we want to investigate, whether or not the larger degree will lead to the larger influence. And second is about the fund size, and also it can be from our intuition. If the fund has a larger size, then usually the fund should have more influence on the other fund. And also the last is about the return volatility. So that basically measures the fund's performance stability for a mutual fund. So these three covariates are used to measure the influential powers for the mutual fund. So after collect all the data, then the next step is just to determine the which link function we should use, because in this work we focus on the parametric link function. So we have 4 different choices, and here we just recommend to use the exponential link function. And the idea is inspired by the non-nested test. And because obviously these 4 link functions are not nested, so we cannot use the nested test to obtain which one we should use. And the basic idea for the non-nested test is basically to use the link function which corresponds to the largest log likelihood. And the theory can be established, but it's not the focus of this work. And in our case, we just try some simulations to be more convinced. And in the simulation, the true model is actually from the exponential link function. We just want to see under the true exponential link function model, what will happen for the log likelihood if we use the exponential, logistic, and also probability extreme link functions to estimate. So we basically find that as n increases, the percentage that the exponential link the log likelihood of the exponential link function is larger than the log likelihood of the logistic or the other link function will tend to 100%. So in that case, it kind of convinces us to use the largest log likelihood to determine which link function we should use in this case. But if we have the semi-parametric or non-parametric model, then it's kind of straightforward. We just need to test which model we should use. So in this case, we just consider this very simple method and determine to use the exponential link function. And then we just have our kind of standard. It's quite similar to the standard linear regression model model estimation table. So the difference here is that for the standard linear regression, we only have the mean covariates. But for the adaptive SAR model, we also have the influence covariates. So for the mean covariates, I think all of those coefficients have interpretation exactly the same as the interpretations in the finance literatures. And what we care about most here is the interpretation of the coefficients for the influence in covariates. So here, firstly, we obtain 2 significant coefficients, the coefficient of degree and the coefficient of the volatility. And for these 2 coefficients, we have the quite easy understand interpretation. For instance, for degree, so that basically means if we control the other variables, the degree has a significant, I think, positive significant influence on the influential power. So that means the larger the degree and the larger the influential power will be. However, we need to control the other variables. And similarly, the volatility measures the stability of a mutual fund. So if the mutual fund is more stable, so that basically means less volatility, then the mutual fund should have a larger influential power. So all of these results are consistent with our intuition. So that basically means our model is kind of consistent. I think even though it's a model, it's kind of consistent with the intuition and the theory. But what we need to be careful here is that all the analysis is based on the analysis when the other variables are controlled. So in that case, we actually have the interaction between the degree and volatility on the influential power, but not a single effect from the degree or single effect from the volatility. So later I will use some visualization to show you that it's actually a combination of the effect of degree and volatility, but not a single variable in this specific case. And also we have tried our tests, and all the tests just say we should reject the null hypothesis. And I think you may have already forgotten the null hypothesis. The null hypothesis is basically this classical homogeneous SAR model. So because we reject the null hypothesis, so that basically means we should use our heterogeneous adaptive SAR model. And I have already shown this plot after we obtain our parameter estimation, we can actually estimate the influential power, and then we can just sort the influential power, and then we can use those tests to help us to classify or to cluster different nodes based on the influential power. So here is a very ad hoc analysis because we sort the indices first and then we perform the test. And here, if we consider this kind of pair test, and we can find that, so the first p-value corresponds to the first pair, the 1-2 pair, and the 1-2 pair, we can find that the p-value is quite small, so we reject the null hypothesis. So that basically means the influential index of node 1 is significantly different from the influence index of node 2. So in that case, we should kind of separate the node 1 and node 2, and we obtain these different clusters basically based on the p-values. We can alternatively have some other clustering method. For instance, we can conduct k-means method, and I show the result in the paper. So there is a slight difference, and if you are interested, you can just check the paper. So instead of this kind of the sorting influential indices plot, we can also have this visualization of the social network, which can actually give us more intuition about the data. So in this data, I actually have the 409 mutual funds, so I can actually plot them in a social network. And here, I just use different colors and also different size of circles to represent influential power and also different clusters. And obviously, the larger the circle size is, the larger the influential power it represents. So clearly, we can find that the most influential node is actually not in the center of the social network. So really, by using this algorithm, if the node is in the center, so that basically means the node has more links to the other nodes. So that basically means the most influential node does not necessarily have the largest number of links. So it's kind of not consistent with our intuition, but also it confirms our theory here is that the influential power is actually a combination effect from the degree, the number of links, and also the mutual fund stability. So that basically means the degree itself cannot determine the influential power. So we actually need other variables to determine the influential power. So that's the one conclusion we can obtain based on this plot. And the second conclusion we can obtain this plot here is that if we have a look at the sub-network of these top 8 most influential mutual funds, so in this case, we can find that they are almost connected to each other, especially for the most influential mutual fund. It connects to all the other 7 most influential mutual funds. So that gives us another conclusion that to be influential, you do not need to connect to all the nodes in the social network. You just need to connect to the influential nodes in the social network. So that's the other result which can be obtained from this visualization. So I think I spent a lot of time in talking about the real data. So I have several minutes, so I will briefly talk about the simulation. So basically the simulation just confirms our results. So we have the normal setting for the simulation, but in our paper, we also tried the non-normal setting to show the robustness of our estimation method. And here is the result, which is quite small. So I just showed an enlarged one. So it's quite clear that with the increasing of n, we have the decrease of bias, standard deviation, and the root mean square error. So that confirms the consistency of our parameter estimation. And instead of the parameter estimation, we also confirm the statistical inference results in the theory. And here we focus on confirming the empirical powers and also sizes for our test. Remember that we have 3 tests. So we use circle to represent the likelihood ratio test, use square to represent the word test, and we use cross to represent the score test. And for the power, so the powers are shown in the top panel of this plot. And obviously for the powers, all the powers go to 1. So that basically means on the reasonable signal, our test is very powerful. And instead of power, we also verify the size. So for size, when n is very large, then we have this the empirical size is consistent with the nominal size. So the nominal size is represented by using this benchmark. And however, if we have finite sample, especially we have small sample, so in this case, we can find that the score test performs the best. So when we have the small sample, so we recommend to use the score test instead of the other 2 tests. So that's kind of the finite sample performance of these three tests, even though these three tests are asymptotically equivalent. However, their finite sample performances are different. So I think I've basically finished what I want to talk about. So let me just summarize this work. So this work is actually not a very difficult work, both from theory or from the method. I think the only contribution of this work here is that it just involves more of common sense in the modeling instead of only considering the homogeneous influence index, I think, in the classical SAR model. So by involving heterogeneous influential indices, we can actually use those heterogeneous influential indices to identify the influential node, and also we can study what kind of attributes can determine the influential power of a node. So in that case, we can take a more look at those attributes such that we can use those information to help for instance, in our case, help our investment in finance. So I think that's the conclusion, and I think that's the end. And thank you so much. And if you have any questions, you can directly unmute yourself and ask me. Thank you.